Hey there, Stat200. This office hour I'm going to be talking about probability distributions. If you're not quite sure what that is, just kind of break it apart. We're going to be talking about the distribution of probabilities, and we're going to talk a little bit about the normal distribution. We'll talk about the binomial distribution. We're going to use some Minitab Express, and I'll show links to those in the lesson folder. Okay? Let's get started then. Using the standard normal table, find the probability that a z-score is less than negative 2.56 or greater than 1.51. I find it's really easy to use this table if you can visualize what it is exactly that you're looking for. So, what I do is I draw the normal curve, which if you've read the notes, you should be familiar. It looks like that, right? Looks like kind of a bell shape, people like to call this a bell shape. And then there's just kind of the baseline. And key thing to know about this bell is that the area under this curve, if you've taken calculus, this will make it a little bit easier to understand, but the area under this curve is going to total to 1. Alright? On this axis here, we have different values for the z-score. And what the z-score is just the number of standard deviations away from the mean that you are. Right? So this is 2.56 standard deviations below the mean, and this is 1.1 or 1.51 standard deviations above the mean. That's what we're talking about here. We want to find the probability that a z-score is less than negative 2.56 or greater than 1.51. So let's draw where those are on the table. Negative 2.56 is pretty far down. It's probably like here. So we'll call that negative 2.56. We want to know what's the probability that the z-score is less than that. So it's going to be this region over here. Imagine this line extends and goes down. And So we're going to find this area here. And we're also going to find the probability that the z-score is greater than 1.51. So it's not as far from the mean as 2.56. It's maybe right there, 1.51. So you'll note that the negative number here is to the left, positive number is here. 0 would be right here. A z-score of 0 means it's 0 standard deviations away from the mean, which means that it is equal to the mean, right? So we want to find the area, we want to find the probability that a z-score is less than negative 2.56 or greater than 1.51. So, to reiterate, area under this whole curve is equal to 1, right? It's equal to 1. But we want to know what's the area here and here, right? This is less than negative 2.56, this is greater than 1.51. That's what we're looking for. So we know that the answer has got to be between 0 and 1, right? And we kind of intuit that it's going to be kind of a small number. We're missing this huge lump in the middle here, right? So right away, I could go look at the answers and say, well, it's not going to be this one, and it's not going to be this one, right? Those numbers are too big. We're looking at too small an area. It's not going to be big. It's going to be either 0.847 or 0.0707. So, how do we find this? Well, this table right here, which I've copied and pasted, is the same table you're going to use. And what this table does is, if you imagine the normal curve again, here's the normal curve, not to scale. What the table does is, say you give it a z-value. So you say, here's your z-value, you give it to the table. And here are the z-values here. Right? Here's how you're going to find the z-value. What the table gives you is the area to the left of that z-value. Okay? That's how that works. So how do we use that to find these two areas here? Well, for the negative 2.56 one, that's actually really easy. Right? We're just going to say z is equal to negative 2.56, and we'll find that probability. So we'll find this right here. So let's start with that, because that's easier. Alright, so let's look at this table. We're looking for negative 2.56. So we're going to come down this column and get to negative 2.5, right? That's where we're going to start. but it's negative 2.56. We're going to go down here, right, until we get to here, right? This is in the 0.06 column. It's in the negative 2.5 row. So this is negative 2.56 probability, right? Here's the probability, 0.0052. And that's it. So let's come up here and write this is equal to 0.0052. All right, so we've got the area in this little tail here. Now we got to find the area in this tail, 1.51. Now remember, this table only gives us area to the left, and the area total here has to be equal to 1. So that means if you can find the lower tail area and you can subtract it from 1, that will give you the upper tail area, right? So we want the upper tail area here. So first let's find the lower tail, the 1.51 lower tail. Let's go to the table, 1.51. Alright, coming down here, 1.5. Here's 1.51. See, it's in the 0.01 column. So there's the probability associated, the left-hand probability associated. So what we want here is we want to find the right-hand associated probability, right? So what we need to do is we need to subtract that from 1. So in order to find that, this probability over here, this area, we're going to need to do 1 minus the value in the table, which is 0.9345. Right? So you can go to a calculator, or if you can do it in your head, that's great. That should be 0.0655. Okay? So now we know the probability here, we know the probability here. So what we're going to do is we're going to just add these two together, add that and that together. Alright, so it's going to be 0.0052 plus 0.0655. Alright, which is going to be equal to 0.0707. And won't you know it, that's an answer option right there. And that's how you come across it. So it's best to visualize what you're looking for, what the table's giving you, and with those two you can figure out the answer. Let's move on. That's a pretty tough one. Alright. Suppose that a student needs to buy 6 books for her history course. The number of books that she will be able to find used is the binomial random variable x, with n equals 6 and p equals 0.30. In other words, the probability that you will find any given book used is 0.30, or 30%, and is independent from one book to the next. See that? Pay close attention. Independent from one book to the next. What is the probability that you will find more than 2 used books? Well, what I want you to do here is I want you to use Minitab Express. That's the fastest and easiest way to get it done. So what you do, and I'm going to post a link to the video, is you're going to go into Minitab, you'll specify all this information, and it'll spit this out for you. And there's the answer right there, 0.744. But if you didn't have that, how could you do this? So, in other words, the probability that you'll find any given book used is 30%, and they're independent, right? I kind of highlighted that. If you remember from the probability lesson, if you have independent events, you can multiply their likelihood together, right? So what does that mean? We're going to try to find the probability that you'll find more than 2 used books, which means it's going to be either 3 or 4 or 5 or 6 books that she can find used, right? So that's pretty tough to calculate. That's a lot of stuff to write down, but what you could find is the probability that she finds 2 or fewer used books, right? So if she finds 0 used books, that means we have 0.30, oh, I'm sorry, that's wrong. That's the chance she gets a used book. The chance that she doesn't get a used book is 1 minus 0.30, which is 0.70, right? And that, if it happens with all 6 books, you can raise that to the 6th power. That just means I'm multiplying this by itself 6 times. So 0.7 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7. Or you can plug this into your calculator. It's a lot simpler. So that's the probability of getting 0 books, 0 used books. What's the probability that she gets 1 book that's used? Well, that's going to be 0.70 to the 5th, right? We have 5 new books that she has to buy times 0.30. That means she gets 1 used book and 5 new books. And finally, the probability that she gets 2 used books is 0.70 raised to the 4th times 0.30 raised to the 2nd power. So if you know how to calculate these, you can actually plug these in your calculator and add them all together. That's another way to do it. I'm not going to do it here because it takes a little longer, and honestly, I just want you guys to use this nice shortcut. Minitab Express is there to take all of these calculations out of your hands. Okay? And like I said, I'm going to post a video to that in the lesson folder. Let's move on. Joan has noticed that the probability distribution for x equals the number of students in line to use the campus ATM machine when she shows up to use it is shown above. The variance of x, which is v of x, is equal to 1.16. What's the standard deviation of x? So I'll tell you right now, most of this information here is not necessary. We don't need this table here, not necessary. We don't need this story about Joan and what's going on here. All we need to know is in the last 2 sentences. We have the variance of x. What's the standard deviation of x? Well, what is the standard deviation of x? Let's write that down. Standard deviation of x is equal to the square root of the variance of x. Well, the variance of x is 1.16. So in this case, it's the square root of 1.16. When we plug that into a calculator, we're going to find that that is approximately equal to, any guesses? 1.08. Alright? It's as simple as that. If you can remember this line right here, that's the key to solving this one. There's our answer. Next question. Suppose that a student needs to buy 6 books for her history course. This is the same setup as before. Now we want to know what's the probability that she'll find exactly 2 used books. And I'm going to post this up online too. This is going to be the second binomial question. So there's a way for you to go into Minitab Express, feed it this information, and this information, and it'll think about it and it'll spit it out for you. But if you ever find yourself on a deserted island and you just have to calculate that binomial random probability, I'm sure a situation we are all afraid of, what you can do is just use what I was talking about before, the probability of getting 2 books used. So 2 used books, I should, I guess, maybe include used here. 2 used books, the probability of that happening. Well, that means she has 4 new books. And remember, she has to buy a new book with probability 0.7, right? Because if the probability she can find it used is 0.3, the probability it's going to be new, 0.7. So 0.7 to the fourth times 0.30 raised to the second power. If you plug that into your calculator, it'll give you the same answer. Sound good? Now of note, it is important to say that because of rounding, your calculator answer might be just a little bit different from the Minitab answer, but you'd be close enough to say, well, yeah, this is the answer. Okay? But you can always just hop into Minitab Express, let it do all that for you. Keep the thinking out of it. Alright, next one. The Southside Bowling Alley has collected data on the number of children that come to birthday parties held at the bowling alley. Let the random variable x equal the number of children per party. The distribution for the random variable x is given above. What is the probability that at least 7 children will come to a party? At least 7 children. Right. So just kind of a quick interpretation of what this table means. So this table is saying, okay, this Southside Bowling Alley holds parties and it never has fewer than 5 kids at a party or more than 10 kids. And the probability of having 5 kids at a party, randomly selected party, is 0.15. Probability of having 6 kids, 0.2, 7.1, 8.25, 9.1, and 10.2. That's what that means. So, we want to know what the probability that at least 7 children come to a party. At least 7, right? So that means 7 or more. 7 or 8 or 9 or 10. Well, all you got to do there, not too complicated, is you just need to add the probabilities associated with each of those. So it'll be 0.1 plus 0.25 plus 0.1 plus 0.2. What do you get? 65? 0.65? That's it. That's all you got to do. You got to pay attention to this wording here. It could be at most 7 children. In that case, you have to do 5 or 6 or 7, right? It could say between 6 and 8 children. That'd be 6, 7, and 8. You just have to know how to use this table to get what you want from it. So that's how you're going to do that one. Next one. A child is observing squirrels in the park and notices that some are black and some are gray. For the next 5 squirrels she sees, she counts x equals the number of black squirrels. Suppose x is a binomial random variable with n equals 5, p equals 0.5. What's the expected number of black squirrels she will see? E of x. Now I'm going to write down here is how you're going to find e of x, expected value of x, for a binomial random variable. For a binomial random variable, the expected value of x is just n times x. Or I'm sorry, I wrote x and got all flustered. Okay, let's use the dot to indicate that we're multiplying. So it's going to be n times p. That's the expected value of x. So in this case, n is 5. Multiply that by p, which is 0.5. You can do that in a calculator or do it in your head. But that's going to give you exactly 2.5, right? Half of 5 is 2.5. Half of $5 is $2.50. So that's our answer, and that's how you do it. It's really simple, really easy. Just remember this little formula, write it on a flashcard, say it to yourself a few times. It's not too complicated. That's how you do it. And next up, and I believe the last one, yes, the last question. Suppose that for x equals the net amount won or lost in a lottery game, the expected value is e of x equals negative 0.50. So negative 50 cents. What is the correct interpretation of this value? Is it the most likely outcome of a single play is a net loss of 50 cents? The player will have a net loss of 50 cents for every single time he or she plays this lottery game. Over a large number of plays, the average outcome for plays is a net loss of 50 cents. A mistake must have been made because it's impossible for an expected value to be negative. Alright. So, let's clear out the low-hanging fruit here. A mistake must have been made because it's impossible for an expected value to be negative. That one's wrong. I mean, that's just incorrect. It can absolutely be negative. In fact, this is how lotteries and casinos make their money. They have a negative expected value for the players. So the casino might make only a few cents every time somebody plays, or, a few cents on the dollar. But it adds up, right? Expected value can absolutely be negative. All right, next. The most likely outcome for a single play is a net loss of 50 cents. While there are certainly cases where that could happen, it's not a good interpretation because it's not necessarily true every single time. Okay? So this guy is out. You can have a net loss of 50 cents be the most likely outcome, but you know what? It probably isn't, because people wouldn't play it if they knew that the most likely outcome was the loss of 50 cents. So that one's not it. A player will have a net loss of 50 cents every single time he or she plays this lottery game. Well, that one can't be true, right? I mean, otherwise it's not a lottery, because you would never win. You would always just lose 50 cents. You'd put money in, you'd lose 50 cents every single time. So that's not it either. So the correct interpretation is, over a large number of plays, the average outcome for plays is a net loss of 50 cents. Right? You can think about this in terms of roulette if you want, and actually I think the Wikipedia page for roulette has a pretty good explanation. And the expected value for your winnings on a roulette play, it's something like, I can't remember. If you bet $1, your expected value is something like you lose, I want to say it's like 3 cents, 3 or 4 cents. So it's not a very big loss for you on average. So you might win. You might win $5 or $10 or $20, but if you kept playing, roulette, you gave in to gambler's fallacy, whatever, you kept going, you would eventually find out that on average, you lost 50 cents every time you played. That's what that means. And that's what an expected value is. It's very interesting, and if you're interested in gambling at all, you should go online and check that out. Because that'll let you know, if you think about it, the long run loss of when you gamble. Because they're always going to be lost, otherwise there would be no casinos. They need to be able to fund themselves, right? So that's what an expected value is. It's the long run average. Okay? That's all I have for you for this lesson. As always, if you have any questions, send me an email. And good luck this week.